let's get started. So, let's see. We don't have any problem set, and we'll have our usual problem session. There was a typo that was noticed on the first problem. I think this said the sum over n. This said sum over a. For that, I'll make that correction and make sure that it's clear. Okay. All right. So, last time we talked about one last piece of mathematics that is going to be very important, and this is the ideas of special properties of operators that commute with one another or don't commute with one another. Okay? So if we have two operators that commute with one another, then what we can say is that there exists a basis of vectors which are simultaneously eigenvectors of these two operators. And that is to say that those two operators are simultaneously diagonalizable. Okay? Right? That's to say there is a common basis such that a representation of these two operators in that basis will be a diagonal. Now, of course, we talked a lot last time about all the subtleties associated with degeneracies, and if there are degeneracies in the eigenvalues, then it's not guaranteed that a given one set of eigenvectors of one operator are also eigenvectors of the other. They'll be block diagonal. So if in the blocks associated with the non-degenerate eigenvalues, but then we can always rediagonalize within those blocks, and therefore there exists always a common basis of eigenvectors for commuting operators. Okay? And then furthermore, what we discussed was this idea of a mutually commuting set of compatible operators. Actually, that's not quite right. This sort of says the same thing. What I mean to say is a complete set of mutually computing operators. So what do I mean by that? What I mean by that is, let's suppose I have a set of operators that all commute with one another. Okay? They're mutually commuting. They're said to be complete if the state of the space, of the Hilbert space, can be specified uniquely as the common eigenvectors of these set of operators. Okay? And we gave the example of in angular momentum, the magnitude squared of the operator and some one component is a complete set of mutually commuting operators. That is to say, every state is specified as a simultaneous eigenvector of those two operators. If I just told you one of those operators, and I said find its eigenvectors, well, that won't tell me uniquely what the state is because of degeneracies. But by specifying both of these, I'm guaranteed there's only one state. Okay? And that's going to be, that concept will be important when we put the hooks on this abstract theory back into physics. The number of operators one needs in order to uniquely specify the state of the system as a simultaneous eigenvector is related to the number of degrees of freedom, physical degrees of freedom in the system. So for example, you know about the hydrogen atom. if I think about the hydrogen atom, forgetting about spin for the moment, and I ask you, how do I specify the energy levels of the hydrogen atom? Well, I need the principal quantum number, I need the orbital quantum number, and the magnetic quantum number. N, L, M are the three quantum numbers that you need to spot. Why are there three? Because it's in 3 dimensions. The electron, if I fix the nucleus relative to the proton, there are 3 degrees of freedom associated with the motion of the electron. So we'll make that connection more deeply as time goes on. All right, very good. So now we're finally at the stage. We've spent this beginning part of our school year talking about some of the mathematics that we need in order to analyze quantum problems. And so now what we want to do is lay out the structure of quantum mechanics. Very important. So, you know, in some sense, where this structure comes from, and you know, what are sort of basic principles from which the structure of quantum theory arises, is still an area of active research. You know, are there some sort of basic axioms, basic principles, which you just say those, the rest of the structure kind of emerges? And we have theories like that. We have relativity, for example, right? Relativity has a couple of basic postulates. The speed of light is the same in all inertial reference frames, etc. And we can kind of derive the Lorentz transformations, etc. So quantum theory, we still kind of grappling what is really the essence from which quantum theory arises. Maybe we're getting a little bit closer. We'll see. We'll talk about that. But what do we demand from quantum theory? What does quantum theory need to do? Well, what it needs to do, the goal is predict the outcome of experiments. That's what any physical theory should do. That's why we have physics, is to predict the outcomes of experiments. So you might say, what's different about where is this quantum? Well, it's not any different from all of physics. I mean, to the degree to which we say that all of physics is fundamentally quantum theory and nothing else, then everything else is sort of an emergent phenomenon out of fundamental quantum theory. Then what we want quantum theory to do is what we want physics to do, period. Predict the outcome of experiments. So, how are we going to do that? So, the structure that we're going to use was really at some level laid down at the beginning. Okay? So there's the so-called Copenhagen interpretation. I mean, as we know, the reason that this is a challenge anyway, and why we use funny words like interpretation, we don't have the Hamilton interpretation of classical mechanics. I mean, classical mechanics is classical mechanics. The term interpretation means there's something which still doesn't quite sit well with us, or in some ways feels incomplete about it. Well, of course, see where those things are. But what the Copenhagen interpretation is an operational interpretation of measurement. What I mean by operational, it doesn't, in some sense, give you a philosophical or deep nature of the world interpretation. It just says this is what you do. Okay? And we're going to try to connect that to how we should think about these things as we go on. So what are these operational tools? These operational tools that we're going to develop. Okay, so the first tool we have is something we call the state. Okay, so this is our first tool. And what is the state? The state is a mathematical tool or mathematical object from which we can calculate the probability for the outcome of any measurement we will do. Measurement one can do on a system. So really we should sort of say the state of the system. So there's some physical thing we're calling the system, and to it we assign a state. State's a mathematical object, and we use it to calculate the probability for any measurement one can do. Okay. Now, there's a particular subclass of states which you may or may have heard about before, which I'm going to call pure states. Pure states should not be confused and is not the same word as eigenstate. That's not what I mean. Okay? There are some people of my generation of older who were taught to have some confused language about pure states and mixed states and eigenstates and non-eigenstates. That's not what this means. Okay? Nipping that in the bud. Pure state doesn't mean eigenstate of some operator. So what do I mean by a pure state? A pure state is so these are states that we assign to a system if we have maximal possible information. Okay? This term about the word information is going to keep popping up in our description of quantum theory, because in some sense these postulates really are, there's very little physics at the moment that I'm talking about. This stuff, I mean, you don't have to know any physics. Anything on this board, where the heck is the physics? So there's a piece of quantum theory, in some sense, that is information theory. It's sort of, in some sense, independent of the platform that we're talking about. And that's been a very interesting development of the last, 20, 30 years. The relationship between quantum theory and information theory. Let me say something close to my heart, so we're bringing that into the classroom here. But let me just emphasize what this means. It means that I've prepared the system as well as physics allows me to. Okay? It doesn't say that it's an eigenstate of position, or it's an eigenstate of momentum, or it's an eigenstate of energy. It just says I prepared it in some way with devices that weren't noisy in any way. It was at zero temperature. Okay? It's the equivalent in classical mechanics as a point in phase space. A point in phase space is a pure state. That means that's the maximum possible knowledge you can have about a classical system. It's that point in phase space, and then it undergoes some trajectory. If I don't know where it is, of course, it's some uncertain bubble in phase space. Okay? But a pure state is the equivalent in quantum mechanics of a point in phase space. And if the state is prepared in a pure state, then what the structure quantum mechanics says is that to this we assign to a pure state, every pure state is assigned a vector in Hilbert space. The dimension of that Hilbert space, we haven't yet talked about what that is, but let's just assume it has some dimension. So let's just say we define, so this pure state, we assign a vector and we typically call it psi. Okay? So this is some vector in Hilbert space. So every pure state is assigned a vector in Hilbert space. This is like, as I say, a point in phase space. All right? And what this is as we remind ourselves, this is the mathematical object from which we calculate all probabilities of outcomes of any measurement one can do. All right. What else can we say about this state? Well, really, what we have is really, there is an equivalence class. That is to say, psi and some constant times psi. This is a complex number. Remember, we're talking about Hilbert space. Our scalars are complex, are the same state. So we really should say, instead of a vector, we really should say array. Moreover, so in order to restrict this equivalence class, as you know, we take as our convention to restrict this. By normalization. So we pick within this class of states to represent the state, to choose it to be a unit vector. Have length 1. Okay? So if it's not normalized, we could just divide by its norm and make it norm 1. Okay? As we've discussed, that doesn't nail it down completely, because if this state is normalized, so is this. So, in some sense, there's still an ambiguity, there's still an equivalence class of vectors in Hilbert space, all of which represent the same state, even if I restrict it to be normalized. So this overall phase is unphysical. And what it means by unphysical is that it in no way affects our prediction of outcomes of measurements. That's what we mean by physical. If it affects our prediction of an outcome of an experiment we can do, then we say it's a physical effect. It's like, as you know, the gauge in electromagnetism is a mathematical thing. We have different gauges of, say, the vector and scalar potential E and M, but they don't affect any of the predictions of the trajectories of charges because the forces depend on E and D. So it's a mathematical thing, but it's not a physical thing. Okay, now even though the overall phase of the state is unphysical, doesn't mean that all phases are unphysical. For example, let's think about the simple example we've been studying for the last week or so. If we look at spin 1/2, and let's say I have some pure state, psi. That state I can expand, say, in a superposition of the basis vectors spin up and spin down along the z-axis. Okay? Now, these are complex numbers. So alpha has some magnitude and some phase, and beta has some magnitude and some phase in general. Now, the overall phase doesn't matter. It's unphysical. So that means that this state is equivalent to, well, let's say, first of all, let me just factor out the phase of this. Right? It has factored out that one phase. This is unphysical. I can set it to be, this phase to be 0 and set this factor to be 1. Because it doesn't matter. The overall phase can be whatever I like. However, this phase matters. It's very physical. For example.
You wrote me twice.
Yeah, I do that, don't I?
So I have no phase.
So let's go to that case. All right, so this is what it should have been, right? Thank you. Let's suppose, in other words, what I mean is very physical means that there's a very different physical effect. There's a different interpretation of, so there's a different measurement outcome that I can see depending upon what that mathematical value is. If this equals this, then the state is this. Let's let alpha equal beta. And if alpha equals beta, what does it have to be if it's normalized?
Half.
But this is
what are we square root?
Exactly. Because it must be the case, normalization says that alpha squared plus beta squared is 1. Okay. So if this is true, then this is the state. Right? And what is that state? From your homework, you might have seen that particular state. It's the state that's spin up along the x-axis. Okay? So if I were, for example, to measure this along, and the probability that I'll find this spin down along x is 0, because this is spin up along x. However, if alpha is beta is 1 over root 2, and say the difference between these phases pi over 2, then this state is what? Well, it's 1 over root 2 plus I. And what is that state?
Y?
Yeah, that's spin up along y. That's a state that if I were to measure it along x, I could get spin down along x. So there's a very different physical measurement, a very different outcome. So there's this relative phase between the probability amplitudes in a basis matters, but the overall phase doesn't. How many parameters, real parameters, does it take to specify a pure state of spin 1/2? So a pure state, so the spin 1/2 is specified by what? Well, if I look at this expression over here, I need to specify the relative phase. That's one parameter. And then I have alpha and beta. But alpha and beta are not independent. The magnitude of alpha and magnitude of beta are not independent because we have normalization between two parameters. Okay.
So where's the alpha, psi beta and psi alpha are dependent on each other? Or they're combined to one new variable, the relative phase?
They're combined into one new variable, the relative phase. So it's specified by two parameters. And the way we saw that is that we have two complex numbers. So that's 2 times 2 real parameters. Right? Because each complex parameter has a real and imaginary part. Minus 1 for the overall phase. Minus, we take away one parameter because one of the amplitudes is defined in terms of the other by normalization. So the number of real parameters that I took, this is 4 minus 2 is 2. Okay? In fact, what that parameter is, as we will see about the next time, is just what is the direction on the sphere that the spin is pointing. And that's specified by 2 angles. It's another way of specifying this. Because we see here, this guy is spin up along x, this guy is spin up along y. Every pure state of spin 1/2 is spin up along some direction. So all if I just tell you what direction it is, I know what the state is.
So mixed states are spin down?
No. The term mixed should not be confused with superposition. Again, pure does not mean eigenstate. All of these are pure states. Of course, they're eigenstates of something. But it just means that I have the maximum possible information. The term mixed state, 7 more points, and we'll get to that next lecture.
So pure states cannot be done, right?
They can. They're spin, it's because spin up along some direction is spin down along minus it, right? So if I have, say, spin up along x, or spin up along z, this is spin up along minus z, which is the same thing as down along z. Yeah?
So what are the 2 degrees of freedom? I mean, is it like the direction you're measuring and then where it is along that? Or, because I mean, you give the example of the electron in the orbit, I can visualize 3 degrees of freedom in space.
Yeah. Well, of course, this, as you know, spin is not a orbital degree of freedom. As to say, it's not associated with physical space.
Okay.
So this is an abstraction.
Okay.
There's no way to think about those degrees of freedom in terms of our standard. It's a new degree of freedom. All right, so now I have a question for you. Given a pure state in a d-dimensional Hilbert space, okay, this was a two-dimensional Hilbert space. But suppose I have d dimensions at spin 1, something like that. That has, as you know, 3 dimensions. How many real parameters does it take to specify a pure state?
D.
D. You might guess that because this was 2, and it's a good deduction, but it's not quite right. You should think about this argument. So generally, we might say the state is expanding. We can expand it in a basis, right? So let's just think about it. So I have D basis vectors, and I have D complex amplitudes.
So 2 times D?
Oh, so it's
2 times D is the number of complex amplitudes, right? However, I still have the overall phase. I can subtract that, take that out. I don't need to specify that, so I can factor that out. And I also have normalization, which means that all of these guys have to add to 1, which means that one of the magnitudes can be expressed in terms of all the others, can be removed.
D minus 1.
So it's 2D minus 2. This is the overall phase is irrelevant, and this is normalization. So for the case of spin 1/2, D was 2, this was 2. Yeah?
What if you, let's say D was 3?
Yeah.
And you only do one of the constants, like alpha, beta, and delta. If you only do alpha, you didn't know beta or delta, you still need one more degree of normalization, right? Or that, or
What I'm saying is, suppose I had, let's say I have, as you said, a state which is, let's call it, okay, there are these 3 basis vectors, 0, 1, and 2. Okay? How many real parameters do I need? Well, I can factor out the overall phase. So let me do that. I'm taking that one to be the phase of this. So this becomes beta E beta minus alpha. And then I have gamma minus alpha. Right? So that's equivalent because I just got rid of one phase. That's the same state. Moreover, so right now I have 1, 2, 3, 4, 5 parameters to specify state. But that's not quite true because I could just say, instead of alpha, I can write this as the square root of 1 minus beta squared minus gamma squared. So I have instead 1, 2, 3, 4 parameters, right? Which is 2 times 3 minus 2.
so you have to original 2 of the constants, right?
What I'm saying is this is how many parameters you need.
Oh.
Okay. If it's a pure state. All right. Good. So that's the state. Of course, there's another piece, and this is, in some sense, not really, though we write it from the original Copenhagen interpretation as an important postulate. It really isn't. It doesn't really affect this operational definition. of how we calculate the probabilities of outcomes and measures, but I'll state it anyway. And that has to do with observables. So, what do we mean by observables? So what the Copenhagen interpretation says, I'll state it in a slightly different way than my typically state, which says, every permission operator is associated with a physical quantity that one can measure, i.e. observe. Okay? It's sometimes stated the other way around. Anything that we can observe is associated with the Hermitian operator. That's not quite true. That is to say, there are observables that are not, for which there is no permission operator. You didn't know that. For example, yeah. I'm observing the time. Maybe it's wrong, but I'm observing the time. But there's no mathematical object that can, for reasons we'll describe. That doesn't mean that we can't observe it. It means that somehow we've been taught the wrong thing. That every measurement is somehow associated with eigenvectors of permission operators. It's not true. But it is true that every permission operator is associated with the measurement I can do. Right? And examples of this are the standard, physical quantities that we're familiar with from classical mechanics, like energy, momentum, and position, and angular momentum. But of course, there are new physical quantities, and we alerted to this, which don't have this space-time kind of classical property like spin. There are new kinds of air. I should also note there are observations one can do, or measurements, that are associated with non-Hermitian operators. For example, okay, take a look at me.
Velocity?
You just measured my position and momentum at the same time. You did it. Well, maybe not precisely, but you looked at me, you saw where I was, and you saw how fast I was going. So who says you can't measure position and momentum at the same time? You just did it. It's just not associated with the usual kind of measurement you learned about quantum mechanics, but you did it, and everything we do is quantum mechanical. All right, come back to that. All right, let's see. Let me remind myself where I was going next. Right. Oh, yeah. Measurement outcomes. Okay, so this says that the eigenvalues of a Hermitian operator, let me call that operator capital A, the eigenvalues so the eigenvalues, let's call that set little a, Hermitian operator big A, correspond to the possible, I'll call them sharp or fine-grained measurement outcomes one finds when one observes A. Okay, what do I mean by that? So, if one somehow, in ways that we'll try to explain, does a measurement that device is designed to measure the observable A, and we want to know what outcomes that measurement device can find, well, of course, that measuring device may have some intrinsic noise on itself, right? It's not necessarily going to give particular values because devices are often imperfect in some way. But if it can give the sharpest possible values, the most fine-grained values it can find are the eigenvalues of that observable. So what I mean, one of the things, and I'm elaborating on these postulates in ways that you perhaps have not seen in your earlier courses, making them a little bit more refined and modern, frankly. Not every measurement that one does is of this sort. I mean, when I just, did my little jog down there, you maybe made some estimate, but it wasn't a sharp measurement of my momentum and my position. It was uncertain in some way to you. So not every measurement you do is of this sort. But if you do try to devise a device to make the sharpest possible measurement you can make, the values you will find are the eigenvalues of the observable. And those, in this case, are real numbers. Okay. And now we come to an important rule, which is what we want to do, what we said is the goal here is to predict the outcomes of experiments. Okay? So the next thing is, so we do an experiment somehow, we haven't said what this is exactly, just there's some device that does this thing, and it finds one of the eigenvalues. Okay? And we want to know what's the probability of finding a particular measurement outcome. All right? And this is the whole story. What we have is the Born rule. So suppose we assign psi as the state of the system. Okay? Suppose A is an eigenvalue of the operator, the emission operator, capital A, associated with a non-degenerate eigenvector, a ket. Then the probability to observe outcome A, I'll call that little piece of A, is equal to this complex amplitude squared. That's the Born rule. Where the Born rule comes from remains a mystery. But it was motivated, as we saw, and as I would like you to review in the first lecture, where we talked about probability amplitudes as related to wave amplitudes and fractions of intensities. But it was motivated from that and then became the rule that worked. And we, to this day, still try to see to where this really comes from. We don't know. All right, now, a few things I'd like to say about this. Okay, so I guess so remember, so psi itself is expandable in the basis of the eigenvectors of the Hermitian observable, because the Hermitian observable, because the observable is a Hermitian operator, and we know that all Hermitian operators, their eigenvectors form basis, it means that I can always expand any vector in that basis, okay? So what that tells me is that this projection is just this amplitude. So the probability to see the outcome A is this probability amplitude squared. It's another way of writing the same thing. Right? Moreover, when normalized, we assumed psi is normalized. Right? Which means that if it's normalized, the sum of all of, by the Pythagorean theorem, the sum of all these guys is 1, which is to say this total probability to find something is 1. If it wasn't normalized, we could use the same rule, but we just have to divide this by this. And that would just automatically make this a probability. If a probability, remember all probabilities are numbers between 0 and 1, and the total probability has to add to 1. Okay, very good. So the probability of some outcome happening, something's going to happen for this measurement is definitely 1. So I made this point here about non-degenerate eigenvectors in my particular way of writing down the Born rule in its most elementary form. But we're going to get increasingly sophisticated about the Born rule. What if A is a degenerate eigenvalue? So let's say that there is a set of eigenvectors, I'll call them u sub a I, where I goes from 1 to some degeneracy factor bigger than 1, such that all of these have the same eigenvalue. What is the probability? So again, suppose the state I assign to the system is the ket psi, and I want to know what is the probability of finding measurement outcome of observable capital A, this. I want to know what is the probability of finding that. Well, the answer is you can't tell me because I haven't given you enough information. It depends on what the measuring device does. If I have degenerate eigenvectors, it means that there are actually other quantum numbers, other mutually commuting observables that I would need to completely specify which one of these vectors in this degenerate set I'm talking about. So, if the measuring device doesn't distinguish between the different other eigenvalues that are necessary to specify which state I'm talking about, then so let me write these things down. To fully specify which UA I'm talking about, we need to specify we're running out of batteries?
No.
Oh.
I thought it was calm.
So to specify which one of these guys I'm talking about, if I wanted to take that inner product according to the Born rule, I need to specify other eigenvalues of a mutually commuting set. But suppose, so there's two possibilities I might consider. If the device doesn't measure the other observables, Well, it doesn't know which one it got. In that case, the total probability would be the sum over all the possible probabilities associated with that outcome. So in this case, what it's saying, the device, in principle, for example, again, I'll come to your question in a moment, Stephen, let me just finish this thought. Let's think about angular momentum. If I have a device which measures the magnitude of the angular momentum but doesn't tell me what direction the angular momentum was in, then I have to sum over the probabilities of all the states, all the LMs with the same L, but all the possible M's. Right? Because I add the probabilities because those different alternatives are in principle distinguishable, but I don't know which one happened. Okay? On the other hand, if the device measures also a compatible observable B, which commutes with A, then the probability depends on both the particular outcomes. Let's just say there were two. Say that completely. Say that the complete set is specified by two observables. Okay. So it's not enough. The Born rule, as it's typically stated, is stated for what we are really typically stated for the case where you have a non-degenerate eigenvector. But if you have degeneracies, it's already subtle. Yeah, Stephen, you have a question.
And also, there are two lines above the devices. It looks like you have stopped one and started a new one without finishing the thought.
To fully specify which this I'm talking about, we need to specify something. We need to specify the other eigenvalues of a mutually commutative set. All right. So, now the Born rule, as written here, are examples of projective measurements. Why do I call them that? We call them that because there's a relationship between this Born rule and the projection operators. So let's take another look at the Born rule. So let's look at the non-degenerate case. We said the probability of finding outcome A is equal to this. I always assume my states are normalized unless stated otherwise, which is equal to this amplitude times its complex tangent, psi star psi. Everyone remembers psi star psi. And this is the projection operator that projects me onto that direction in Hilbert space. So another way of writing the Born rule is this. Okay. in this case, because it's a non-degenerate eigenvalue, this is a one-dimensional projector. It's a projector onto a direction in Hilbert space. Okay. On the other hand, if I had the degeneracies, and if, for example, doesn't resolve other mutually commuting observables, then this probability we said over here, I'd sum over all the probabilities for all the degenerate eigenvectors that all have that same eigenvalue, which again, I can write taking psi star psi. And then I can take this, because it's linear, the inner product is linear, I can take it outside the sum. Probably made that G for that A. And this again is a projector, but it's a projector not onto a 1D space, but a projector onto the space of dimension G associated with that degeneracy. Okay? Notice because we have a resolution of the identity, that is to say, any observable A, we can resolve the identity in terms of projections onto all the spaces associated with the different eigenvalues, right? That could be a sum of 1D projectors or multiple dimensional projectors, depending on the degeneracy of those eigenvalues. Because of that, well, this is another way of saying that this is a way of decomposing the probabilities. As I say, if I look at the inner product of this is 1, if this is normalized, and this is equal to the sum over A. So we can associate each one of these objects is the probability out of seeing the measurement outcome A. So by having a resolution of the identity, we have a way of assigning probabilities. Because the probabilities are numbers that add to 1, and moreover, these are positive or non-negative numbers. How do we know that?
The probability can't be negative.
Yeah, that's true, but how do we see that from this? This is a projection operator. How do we know that this inner product is always positive?
It's the observables are from a Hermitian, they're always real, right?
Yeah, but really, I'm just asking about the properties of projection operators themselves. I mean, we kind of see this here. Yeah.
I mean, A on psi
Right.
will give you,
Every one of these things is positive. Right. Now, what I want to say is the following. This I'm just going to mention because we should, although we won't get into it too deeply. Yes. Not every measurement is projective. Projective measurements are measurements that are fine-grained. They tell you, are you this eigenvalue? What's the probability of finding it? As we said, sometimes your measuring device can't be that sharp. It doesn't know whether or not it had that eigenvalue. So we want a mathematical structure in quantum mechanics that allows us to assign probabilities to measurement outcomes that aren't, are you this eigenvalue, yes or no? Maybe they want to say, are you this eigenvalue within the uncertainty of an error bar? We should be able to do that. How do we do that mathematically? What we do, what's required is the following. We need some way of breaking down probabilities as positive numbers that add to 1. And what's required for that is we need a resolution of the identity in terms of what I'll call positive operators. Let me explain this. So let's assume that there is some set of operators, I'll call them E. I'll say they're positive. What that means in a moment. What does it mean for an operator to be positive? Such that the sum of these guys adds to 1. An operator is said to be positive if it's Hermitian and all its eigenvalues are non-negative. So suppose I have a set of such operators whose eigenvalues satisfy that. Okay. Then I can, the generalized Born rule is the following. The probability of outcome A is, instead of having the projector, I have this positive operator. That's the Born rule. Every measurement that one can do in the physical world is defined by a set of positive operators that add to 1. You may never have seen this before. Most physicists haven't, but they should, because this is what really is true. Rarely, it's almost impossible to do such a measurement that's really projective. That would require a lot of resolution in your detector. This kind of thing has a very heavy-handed name that's arcane, but which still stands. And it's called a POVM, which stands for positive operator value measure. It has to do with measure theory and blah, 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 but it doesn't matter. It's the thing previously known as the positive operator value measure. We just call them POVMs, so no one even knows what it stands for anymore. But a POVM, so, all right. The difference between a POVM, generally, and a projective measurement is that projective measurements had this connection to observables. The way we did this is we said there's an observable, we want to measure angular momentum. We try to measure it, we find one of its eigenvalues, and the probability we find that eigenvalue is associated with the overlap with the eigenvector, right? General measurements, I'm not saying what these A's are. They're measurement outcomes. We'll look at examples of this as we go. But they're not necessarily the eigenvalues of a Hermitian operator. They're just the possible outcomes of the device. And if it satisfies this property, then I can assign probabilities. And the fact of the matter is, any POVM, there exists a way of measuring these outcomes, and they occur with the probability. So if you have mathematically write down a set of positive operators and add to one, I can go in the lab, or tell my friend, Professor Becerra, to go in the lab and design a device that can measure these measurement outcomes, and they will occur in his device with this probability. All right, so let me spend 5 minutes then simply reviewing a couple of things that you know about. Because what we found here is that one of the things that's strange in quantum theory, unlike classical theory, is that measurement outcomes are generally random. We can only assign a probability for what we're going to see. We can't say for sure, even when we have a pure state. I mean, in classical mechanics, we can have uncertainty too. But if I have, even when I have maximum possible knowledge about the system, every measurement I do isn't necessarily determined. It can only come at random. That's weird. What it means, if we're going to analyze things, we have to think a little bit about statistics. So if I have a random variable, A, which occurs with probability little a, little piece of A, then what can we say statistically? Well, we can look at things like the mean value. Which is the sum over all the values weighted by their probability, right? Now, if this is quantum mechanics and we're talking about, for example, projective measurements, of observables. Then this probability is equal to that. That's the eigenvalue of A, right? Again, my linearity, I can take that outside the sum. And what is this object? Do you recognize it? If it was non-degenerate, you might recognize it. I got all day. What is this in the bracket? This is the diagonal representation of something. So if I told you, what is this operator?
Oh, that's f of a.
Yeah, well, what FF? This is the observable A. Right?
Oh.
So this mean value is this. Sometimes known as the expectation value or the expected value. So the expected value or the expectation value of this observable is given by that. It's something you know. It's re-derived. We also have, of course, uncertainty. But is the fluctuation we'll see in a measurement about so this is defined as the square root of the variance. The variance is given by the difference between the expected value, or the, look at it this way. By definition, it's this. So I look at the average value of these, what are these called? The residuals. How different is the value from its mean squared? That's the variance. This value, when I'm doing this, is with respect to a state. I'm not going to write out the state. So I can write this out. This is this squared minus twice this times that plus this squared expectation value. This is a number, so it can come outside. I have minus 2a times a plus a squared, or a familiar form that you know, the variance is equal to the expected value of the square minus the square of the expected value. Okay, so finally, what we wanted to say, because you need this for your homework, but we'll talk about it more, we derive it, is we have the uncertainty principle. The uncertainty principle states the following. It states the following. The product of the uncertainties for two observables in a given state must be greater than or equal to a half the expected value of the commutator. This is, of course, with respect to a given state. What does this say? It says that if I have two observables that don't commute, if this number is not 0, then in general, I cannot be simultaneously certain about the value I will measure for A and B. That is to say, if this right-hand side is non-zero, they don't commute, and the expected value of that is non-zero, that means for that state, there is no measuring device that can simultaneously, sharply determine the value of A and B at the same time. Of course, we know that in the case of position and momentum, we have x and p, your commutator is on h bar, and this is the famous Heisenberg uncertainty principle, delta x times delta p is greater than h bar over 2. But this version of it is more general. All right, we will continue with that next time. Sorry to go over a bit. We had a big discussion. And see you guys at the following. Now we're finally at the stage. We've spent this beginning part of our school year talking about some of the mathematics that we need in order to analyze quantum problems. And so now what we want to do is lay out the structure of quantum mechanics. Very important. So, you know, in some sense, where the structure comes from, and you know, what are sort of the basic principles from which the structure of quantum theory arises, is still an area of active research. You know, are there some sort of basic axioms, basic principles, which you just say those, the rest of the structure kind of emerges? And we have theories like that. We have relativity, for example, right? Relativity has a couple of basic postulates. The speed of light is the same in all inertial reference frames, etc. And we can kind of derive Lorentz transformations, etc. So quantum theory, we still kind of grappling what is really the essence from which quantum theory arises. Maybe we're getting a little bit closer. We'll see, and we'll talk about that. But what do we demand from quantum theory? What does quantum theory need to do? Well, what it needs to do, the goal is predict the outcome of experiments. That's what any physical theory should do. That's why we have physics, is to predict the outcomes of experiments. So you might say, what's different about where is this quantum? Well, it's not any different from all of physics. I mean, to the degree to which we say that all of physics is fundamentally quantum theory and nothing else, then everything else is sort of an emergent phenomenon out of fundamental quantum theory. The probability for the outcome of any measurement we will do. Measurement one can do on a system. So really we should sort of say the state of the system. So there's some physical thing we're calling the system, and to it we assign a state. State's a mathematical object, and we use it to calculate the probability for any measurement one can do. Okay. Now, there's a particular subclass of states which you may or may have heard about before, which I'm going to call pure states. Pure states should not be confused and is not the same word as eigenstate. That's not what I mean. Okay? There are some people of my generation of older who were taught to have some confused language about pure states and mixed states and eigenstates and non-eigenstates. That's not what this means, okay? Nipping that in the bud. Pure state doesn't mean eigenstate of some operator. So what do I mean by a pure state? A pure state is so these are states that we assign to a system if we have maximal possible information. Okay? This term about the word information is going to keep popping up in our description of quantum theory, because in some sense these postulates really are, there's very little physics at the moment that I'm talking about. This stuff, I mean, you don't have to know any physics. Anything on this board, where the heck is the physics? Period. Then what we want quantum theory to do is what we want physics to do, period. Predict the outcome of experiments. So, how are we going to do that? So, the structure that we're going to use is was really at some level laid down at the beginning. Okay? So there's the so-called Copenhagen interpretation. I mean, as we know, the reason that this is a challenge anyway, and why we use funny words like interpretation, we don't have the Hamilton interpretation of classical mechanics. I mean, classical mechanics is classical mechanics. The term interpretation means there's something which still doesn't quite sit well with us, or in some ways feels incomplete about it. Well, of course, see where those things are. But what the Copenhagen interpretation is an operational interpretation of measurement. What I mean by operational, it doesn't, in some sense, give you a philosophical or deep nature of the world interpretation. It just says this is what you do. Okay? And we're going to try to connect that to how we should think about these things as we go on. So what are these operational tools that we're going to develop? Okay, so the first tool we have is something we call the state. Okay, so this is our first tool. And what is the state? The state is a mathematical tool or mathematical object from which we can calculate. So what do I mean by that? What I mean by that is, let's suppose I have a set of operators that all commute with one another. Okay? They're mutually commuting. They're said to be complete if the state of the space, of the Hilbert space, can be specified uniquely as the common eigenvectors of these set of operators. Okay? And we gave the example of in angular momentum, the magnitude squared of the operator and some one component is a complete set of mutually commuting operators. That is to say, every state is specified as a simultaneous eigenvector of those two operators. If I just told you one of those operators, and I said find its eigenvectors, well, that won't tell me uniquely what the state is because of degeneracies. But by specifying both of these, I'm guaranteed there's only one state. Okay? And that's going to be, that concept will be important when we put the hooks on this abstract theory back into physics. The number of operators one needs in order to uniquely specify the state of the system as a simultaneous eigenvector is related to the number of degrees of freedom, physical degrees of freedom in the system. So for example, you know about the hydrogen atom. If I think about the hydrogen atom, forgetting about spin for the moment, and I ask you, how do I specify the energy levels of the hydrogen atom? Well, I need the principal quantum number, I need the orbital quantum number, and the magnetic quantum number. NLM are the three quantum numbers that uniquely spot. Why are there three? Because it's in 3 dimensions. The electron, if I fix the nucleus relative to the proton, there are 3 degrees of freedom associated with the motion of the electron. So we'll make that connection more deeply as time goes on. All right, very good. So let's get started. So let's see. We don't have any problem set, and we'll have our usual problem. There was a typo that was noticed on the first problem. I think this said the sum over n. This is sum over a. For that, I'll make that correction and make sure that it's clear. Okay. All right. So last time we talked about one last piece of mathematics that is going to be very important, and this is the ideas of special properties of operators that commute with one another or don't commute with one another. Okay? So if we have two operators that commute with one another, then what we can say is that there exists a basis of vectors which are simultaneously eigenvectors of these two operators. And that is to say that those two operators are simultaneously diagonalizable. Okay? Right? That is to say there is a common basis such that a representation of these two operators in that basis will be a diagonal. Now, of course, we talked a lot last time about all the subtleties associated with degeneracies, and if there are degeneracies in the eigenvalues, then it's not guaranteed that a given one set of eigenvectors of one operator are also eigenvectors of the other. They'll be block diagonal, so in the blocks associated with the non-degenerate eigenvalues, but then we can always rediagonalize within those blocks, and therefore there exists always a common basis of eigenvectors for commuting operators. Okay? And then furthermore, what we discussed was this idea of a mutually commuting set of compatible operators. Actually, that's not quite right. This sort of says the same thing. What I mean to say is a complete set of mutually computing operators. So